You see my screen, right?
Yes, I see it. So I'm very happy to introduce our next speaker, Mehdi Soleimanifar from MIT, who will tell us about from communication complexity to an entanglement spread area law.
All right. So thanks for coming to my talk. This is joint work with Anurag, Anshu, and Aram, Harrow. And during this talk, I'll tell you about two seemingly different problems. One is about the communication complexity of testing quantum states, and the other is about the structure of entanglement in the ground state of local Hamiltonian. In this talk, I'll present a connection between these two topics and tell you about the implications. OK, so let me begin with the communication complexity part first. A problem that arises in quantum information theory is when two parties want to test a bipartite state. So Alice and Bob have some shared state psi, and they want to test whether this state is equal to some target state omega or not. So in other words, they want to jointly perform this two outcome POVM that tells them if they have the state omega or not. So the parties also share some number of EPR pairs. And in the rest of the talk, I'll just assume that we have an infinite number of these pairs, which are collectively denoted by this state capital phi. So the way Alice and Bob communicate to perform this joint measurement is like this. They apply local unitaries on their share of the state, the EPR pairs, and some ancilla register, which then they send the ancilla back and forth a bunch of times to achieve the measurement. And the minimum number of qubits they need to exchange to perform this joint measurement is called the communication complexity of testing the state omega, denoted by this C of omega. We're going to actually allow the parties to instead perform an epsilon approximation of this, measured in the operator map. And the communication complexity of this approximate version is denoted by C sub epsilon. All right, so this is the setup. Now, a natural question that you can ask is, what property of the state omega determines the communication complexity of testing it? You might expect that whatever this property is, it has to do with the entanglement in this state. But how can we actually quantify this? So the first simple observation is that if Alice and Bob apply local unitaries on their sides, the communication complexity doesn't change. As a consequence, we can always assume that the target state is in the Schmidt form, which looks like this. Here, these lambda k's are called the Schmidt coefficients, and they form a probability distribution. I'll always assume that these coefficients are sorted in a non-increasing order. And therefore, once you plot them, you get something like this. Here, I want you to remember two parameters of this distribution. One is R, the number of non-zero coefficients, or the rank. And the other is lambda 1, the maximum Schmidt coefficient. So this all shows that whatever this communication complexity of testing omega is, it has to depend only on some property of this distribution of the Schmidt coefficient. To see what property we should be looking for, let's look at some simple examples first. So the first example is when we want to test a product state. So there is only one non-zero Schmidt coefficient in this case. And the testing protocol is very simple. Alice locally tests whether all her state is equal to 0. And she sends the answer to Bob, who then compares this with his own result and decides. So independent of the dimension of the product state, the communication complexity of testing it is just a constant. Now, let's move to a more interesting case where we want to test if there are n EPR pairs shared between the parties. Now we have 2 to the n Schmidt coefficients, and they're all equal. And you might guess that since this is a maximally entangled state and has a lot of entanglement, it must have a high communication complexity too. But it turns out, in this case, the complexity is also independent of n, the number of EPR pairs, and solely depends on epsilon, the approximation error, via this log 1 over epsilon factor. This is a result due to Aharonov, Harrow et al., where they use quantum expanders to devise a testing protocol for EPR pairs. So let's look at a third example, which is a more exotic state, and it's a superposition of the previous two states we have. So it turns out to test this state, you need an order n qubits of communication. And this is because if the parties can implement a coherent measurement for the state omega, they can also perform a reflection about it. And if they can do that, then they can also turn a product state to n copies of the EP operators by just applying this reflection. But it's well known that you need to exchange at least n qubits to prepare n EP operators. So the communication complexity of this measurement is also order n. So to recap, I presented 3 examples where in the top 2, the communication complexity is just a constant. And in the third case, it's proportional to the maximum amount n. So what these examples basically show is that it's not the amount of entanglement that determines the communication complexity, but rather how the Schmidt coefficients are distributed is the thing that matters. In particular, in the top 2 examples where the complexity is low, the Schmidt coefficients are all equal. But in the third example that has high complexity, half the mass is on one Schmidt value and the rest is on some other value, which is this 1/2 to the n+1. So in the general case, the quantity that captures all this is called the entanglement spread. And in its simplest form is defined as the log of rank times the maximum Schmidt coefficient. So it's log of the area of this shaded region in the diagram below. And this was first defined by Haldane and Winter, who also made the connection to communication complexity. Since the rank R is roughly of the order 1/, the smallest Schmidt coefficient, you can also think about this quantity as the log of the ratio between the largest and smallest coefficients, which again highlights why we call it entanglement spread. If all the coefficients are the same, then the entanglement spread is 0. And if the distribution is quite spread out, then this quantity is large. And there is a nicer way of expressing this in terms of the difference between the max and mean Rayleigh entropies. So here, max entropy is the log of rank, and mean entropy is the log of 1/, the maximum coefficient. So one issue with this definition is that it's actually not quite robust. And the reason is that small perturbations of the state, like making an infinitely long and thin tail or adding some mass to the top part, won't actually change the state in trace distance, but can blow up these Rayleigh entropies and therefore the entanglement spread. So to avoid things like this, we're going to consider a smooth version of this quantity. The difference is that now before finding the mean or max entropy, we are allowed to remove an epsilon mass from the probability distribution. Okay, so this is our definition of the entanglement spread. Now let me get back to how this answers our question about the communication complexity and state the main message of this part of the talk, which is the following. The communication complexity of testing a bipartite state is lower bounded by the entanglement spread of that state. Different variants of this result have been proven before by Haldane and Winter, Quidron and Harrow and Wu. In our paper, we also prove a version of it for our own application, and we get an epsilon to the 2/3 in the smoothing, but I'm just going to ignore that during the talk. So one nice thing about this lower bound is that it continues to hold even if we allow Alice and Bob to use unlimited EP operators during their communication protocol. And the lower bound will still only include the state omega. There is no dependency on the EP operators. We actually exploit this in our work to improve some Hamiltonian simulation protocols, and I'll get back to it soon. All right, so far I've only talked about how the communication complexity of testing a state gives us a bound on its entanglement spread. In the next part of the talk, I'll switch to another problem, the structure of entanglement in grounded states, that turns out to be related to what I've been discussing so far. So suppose we have n qubits that interact with each other, and you can assign an interaction graph like this that describes who's interacting with who. The details of how these particles interact is given by a local Hamiltonian. Each local term here corresponds to an edge of this interaction graph. And although I presented them this way, all the results that I'll discuss in the rest of the talk are not restricted to 2 local Hamiltonians, and they apply to hypergraphs and k-local Hamiltonians too. So this Hamiltonian operator has certain eigenvalues and eigenstates. The eigenstate with the smallest eigenvalue is called the ground state. And I'll assume without lots of generality that the eigenvalue of this state is 0. So the difference between the two smallest eigenvalues is called the spectral gap of the Hamiltonian. And we are interested in the case that this gap is a constant independent of the number of particles. We call the ground states that satisfy this gapped ground states, which are the subject of the rest of this talk. Okay, so why do we care about these states? Well, studying gapped ground states is connected to some central problems in physics, like understanding the low temperature properties of quantum systems or different phases of matter. One other thing that makes gapped ground states nice to study is that, very roughly speaking, they inherit the locality of the Hamiltonian. And you can, for example, write them as a low-degree polynomial of the Hamiltonian, as constructed by Arad, Landau, Vezirani. And this low-degree polynomial preserves the locality. So we expect ground states to exhibit different properties coming from the locality. One such property is the exponential decay of correlations in these states, proved by Hastings and Coma, which says that the correlations between two observables A and B decay exponentially with their distance. This locality also implies that entanglement in gapped ground states is also local and short range. So let's look at the ground state entanglement more closely. One way to think about the amount of entanglement in many particle system is to partition the particles into two sets A and B and look at the entropy of the Schmidt coefficient across the boundary. And that's what we call the entanglement entropy. A very intriguing property of this entropy for gapped ground states is that what we call the entanglement entropy areola, which says no matter how many particles you have in sets A and B, the entropy only scales with the size of the boundary. This is rigorously proven for 1D graphs by Hastings and Arad, Landau, Vezirani. And it's tightly connected to algorithmically finding the ground state by using tensor networks. It's conjectured that areola also holds for higher dimensions or higher dimensional lattices. There has been some progress in 2D by Anshu, Arad, Gossett, and on trees by Abrahamson. It also has been shown that for general graphs, a version of this areola conjecture doesn't hold. So this is a result by Harrow et al., who construct a graph with a boundary of size 1, which has an entropy of order n to some constant power, compared to the constant entropy that the areola predicts. So this is like a huge violation of the areola. Okay, so in summary, entropy is one way of characterizing entanglement in ground states, but so far its properties beyond 1D remain an open conjecture. This motivates a general question, which is whether we can find a universal property for gapped ground states that provably hold for arbitrary graphs. One choice, very suggestively, could be to study the entanglement spread, meaning quantifying to what extent the Schmidt coefficients across a cut in gapped ground states are spread out. So this is our main result, which shows that the entanglement spread obeys an areola in any interaction graph. This graph doesn't, for example, need to be a lattice. Remember that epsilon was the smoothing parameter in our definition. And if you want, you can just ignore it in the rest of the talk. It just contributes as a factor of log 1 over epsilon. So this result says that the ability of a gapped Hamiltonian to spread the Schmidt coefficients across a cut is limited by the number of its local terms on the boundary. And you don't get any non-local contribution from other edges or terms. All right, so how do we prove this? Here is where the connection to the first part of the talk on communication complexity appears. The way we prove this is by designing a communication protocol for testing the ground state. And then we're going to use the theorem we had earlier in the talk to connect the complexity of testing protocols to an upper bound on the entanglement spread. So let's see how we can test gapped ground states. Since I assume the ground state energy is 0, what we want is a protocol that measures the energy and determines if a given state has energy less than half of the gap or more than. So one way to measure the energy, as you might have already guessed, is to use the quantum phase estimation algorithm. So in the phase estimation algorithm, we basically use a Hamiltonian simulation operator controlled on some register that is in uniform superposition. It turns out that if we allow t in the Hamiltonian simulation to be order 1/gap and repeat this algorithm for log 1/epsilon times, we basically get an approximate projector onto the ground state. Therefore, we can measure the energy and with the precision of order gap and get our testing. But this is not quite what we want. What we want is to turn this algorithm into a communication protocol. It turns out Else and Bob can always share the ancillary registers. The real challenge for them is to jointly perform this Hamiltonian simulation operator, e to the ith. This is what determines the communication cost of the whole protocol. I'll tell you soon that there is a non-trivial protocol that they can perform to achieve a Hamiltonian simulation for t up to order 1/gap using a communication cost that scales with the size of the boundary over gap. And since the phase estimation is repeated log 1/epsilon times, that means the overall communication complexity is this thing we have on the slide. Now we can go back to the result I presented earlier and get our bound on the entanglement spread, which is the area law that I claimed before. Okay, so the only piece that I haven't talked about yet is this Hamiltonian simulation subroutine. So let's do that. Let's divide the Hamiltonian into three parts, HA and HB, which are acting solely on Alice's and Bob's sides, and the boundary terms, which are presented in yellow. The depth of the usual Hamiltonian simulation algorithm that implements e to the ith scales with the norm of the whole Hamiltonian and t. If you just naively turn this into a communication protocol, then the cost also scales with the norm of the whole Hamiltonian. What I claim is possible, though, is to have a cost that scales only with the size of the boundary. But how can we actually get this? To see why such a scaling is reasonable at all, let's look at the case that the local terms in the Hamiltonian as operators commute with each other. In this case, Alice and Bob can just locally implement this part without any communications, and they can run a Hamiltonian simulation for the boundary part with the claimed cost of order size of the boundary. But of course, this breaks if the terms are non-commuting. There is a recent result by Low and Week that allows us to get around this issue. This is called Hamiltonian simulation in the interaction picture, which you might have seen before in physics. The trick is to recover something like the commuting case by allowing Hamiltonians that depend on time. In other words, there is an operator hi that depends on time, and it basically replaces the contribution from the boundary Hamiltonian we had before in the commuting case. So this operator looks like this. It's the boundary terms that are sandwiched with these other operators. And I'm going to skip the details, but the point is that the norm of this new operator is the same as that of the boundary Hamiltonian. And therefore, it can be implemented using order size of the boundary communications. All right, so this almost finishes the proof of the area law for entanglement spread. There is one more thing I'd like to show you about this. So if you remember, I mentioned that this lower bound on communication complexity continues to hold even when the parties use unlimited EP operators during their communications. We can use this to our advantage to improve this Hamiltonian simulation protocols. The observation is that we really don't care about the time complexity of what Alice and Bob do locally. Our result is information theoretic, and we only care about the number of messages they exchange. So in particular, we can go through the Hamiltonian simulation algorithms and see if we can replace their ancilla state by these free unlimited EP operators we have at the cost of a possible blowup in the time complexity. We do this for the linear combination of unitaries, or LCU method, due to Berry, Childs, Cleve et al. And this helps us remove various log factors from the communication cost and simplify the protocol. We also use this in phase estimation to reduce the cost of sharing ancillary registers. All right, so here's a summary of the main two theorems I presented. Communication complexity upper bounds entanglement spread. And by using phase estimation, we can get a protocol with the size of the boundary over gap communication complexity, which establishes an areola for the entanglement spread. Now, let me briefly say a few other things about our results. The first thing is that when we restrict the interaction graphs to lattices, meaning when the Hamiltonian is geometrically local, we can improve our results using Chebyshev AGSP and get a sub-areola scaling for the entanglement spread, meaning there is an upper bound of order square root of the boundary. The square root comes from just Chebyshev polynomials. We also show that this result is tight. And this turns out to be related to a conjecture in physics due to Li and Haldane that says that if you look at the reduced state of the ground state in a region A, it has a very specific structure. It looks like the Gibbs state of a system that lives only on the boundary. This is a strong conjecture. It's stronger than the areola. And in particular, it implies the entanglement spread must scale with the square root of the size of the boundary, which is exactly what we prove in our work for lattices. One other thing is the relation between our areola and the usual entropy areola. What we show is that the entanglement spread, which is the difference between mean and max entropy, is always small, meaning it scales with the size of the boundary. Now, it's either the case that the mean entropy is also small, like in 1D graphs, which implies that max entropy and therefore the von Neumann entropy are small. And then we get an areola, or that the mean entropy is large, like in the counterexample Hamiltonian of Aram, Harrow, Landau et al. That I showed you earlier. And then you get a violation for the entropy areola. So gapped ground states fit into one of these possibilities. So this is another take-home message of our work. Okay, so I'm almost done. Here are some open questions left by our work. The first is to see if there is any algorithmic implications for our entanglement spread areola, especially when thinking about contracting tensor networks. So this is something that there are indications of it in previous works, like work by Itaira, Anurag, Anshu, and Rahul Jain, and Sirakanal. And we leave it as an open question. The other is to see if there are other implications for our AGSP based on Hamiltonian simulation and quantum phase estimation in learning gapped ground states. And finally, finding other universal properties of gapped ground state is an interesting open question that's worth a study. All right, so with that, I thank you for your attention.
Thanks, Mehdi. Please enter your questions in the chat. We have plenty of time to answer questions. So Srini Arunashalam is asking, can you also give upper bounds on communication complexity in terms of entanglement spread and recover the EPR result of Harrow et al.?
So you can do that, but there are, in terms of other quantities that are related closely to entanglement spread, this is a result by Kudran and Harrow, that they use a slightly different notion called the Earth moving distance and give both upper and lower bounds. I think for specific states, including EPR pairs, you can also do this in terms of EPR pairs, but I don't know if there is like a result that gives that upper bound just in terms of entanglement entropy. Entanglement spread, sorry.
Actually, to follow up on that, so I remember that the Kudran-Harrow results talking about that, in any communication protocol, you can, without loss of generality, replace the entanglement with a bunch of EPR pairs.
Right.
So is there like a direct connection between their result and what you prove here, or is it more in the techniques that's related?
Yeah, it's fairly similar. I mean, maybe in flavor, it's similar to what we did with EPR pairs, that like we have unlimited EPR pairs, and if you share it, like you don't change entanglement spread. So you can just like, go ahead and assume you have it and use it in your protocols. In their paper, they're more interested in seeing what sort of entanglement you can use for improving communication complexity. And this is like a question that classically we have a good idea of how it works, but quantumly is like unclear. Because as you see, it's not like just the amount of entanglement that matters. You have you need to look at more structures.
Mm-hmm. Great. So next question we have is from Zhu Cao. He's asking, can we get communication complexity bounds on testing multi-party entanglement?
Yeah, that's a good question. Our framework only works for bipartite states or bipartite entanglement. It's not clear how you can generalize things like entanglement spread to multipartite entanglement. And I also don't know if the communication complexity part is studied, where there's this connection between testing bipartite states and entanglement spread, whether you can make a connection between testing multipartite states and entanglement. This is a good question. I don't know the answer.
Let's see. So Sev is asking, do you have an idea in mind when you say other universal properties on your open question slide?
So I mentioned this Li-Haldane conjecture that says if you just look at the Schmidt coefficients across the cut, I mean, we know that all the information about the entanglement is encoded in this distribution. We've studied the entropy of this distribution, and our work talks about the spread. That Li-Haldane conjecture is like more general. It says the whole spectrum looks like what you would get from the spectrum of a Gibbs state. So if you have that, you can get like the normal entropy areola. So it's like a very strong conjecture. It would be very interesting to prove that. And it seems that one would also imply some, it has some algorithmic implications in terms of finding ways to more efficiently contract tensor networks. So I think proving Li-Haldane conjecture would be a very nice result.
We have a question from Alex Grillo. He's asking for a clarification. Does the dichotomy that you mentioned say that a gapped Hamiltonian either respects an areola or are far from it, but there's no gray zone? Or is it more of a trade-off?
Yeah, I mean, maybe I made it too extreme. So we have this smoothing parameter. So all the things that I mentioned are like, there's this smoothing in rainy entropies. So if you're fine with that, then you kind of basically either satisfy areola or you're not satisfying areola. But maybe the way that, the part that you don't satisfy the areola is not as bad as like the Aharonov Harrow et al. Result, which is like n to some constant power. But it would be nice to actually prove this without using this smoothing parameter. Like if you can just show that proving an areola for mean entropy implies an areola for the entanglement entropy. What we show is that proving an areola for the smooth mean entropy implies an areola. But yeah, maybe it's not like a perfect dichotomy and just meant it more intuitive.
Okay, maybe we have time for one final question from Alvaro. He's asking, how far is this from giving you a result on the entanglement entropy? Is the problem that you cannot bound the Schmidt rank of the approximate projector only the communication complexity?
Yeah, so for getting an entanglement entropy areola, we need to bound the mean entropy. And that's a huge challenge. It's not like obvious at all how you can do it beyond 1D. And it relates to like these constructions for approximate ground state projectors that we know how to do efficiently for 1D graphs, but we don't know how to generalize to higher dimensions.
All right, thanks a lot. There are more questions in the chat, but we can save them for the roundtable after the session.